We're going to first start by comparing and contrasting quadratic functions, which are new for us, and absolute value functions, which we've seen before. Looking at the graphs, we can clearly see a difference in the shape of absolute value functions, which look like a V and are made up of two straight lines, whereas quadratic functions form something we call a parabola, and it looks a little more U-shaped. It's made up of two curved lines. So the general absolute value function is written like f of x equals a times the absolute value of x minus h plus k, where a, h, and k are all some numbers that can transform the function. You can reference the foldable we filled out earlier this year to refresh yourself on how each of these variables change our parent function. From this function, we know that the vertex is going to be h comma k. The vertex is either the highest point or the lowest point on our absolute value function. So for the parent function, the vertex is just at the origin, 0, 0. The axis of symmetry is the line x equals h. It's the line that you could fold the function over or fold it in half and it'd be symmetrical on both sides. You can also think of this as the vertical line that's coming out of the vertex. For the parent function, that would be the line x equals 0 or the y-axis. The domain for the absolute value function is all real numbers because even though it cuts off on this graph, the lines will continue on forever and ever in both directions. And the range starts at the y-coordinate of the vertex and then either contains everything above or everything below, depending on whether the graph is opening up or opening down. And that is determined by whether A is positive or negative. So now that we've reviewed a little bit about the absolute value function, the quadratic function is very similar. Let's look at the vertex form of a quadratic function. Comparing the two of these, the only difference is that instead of trying to find the absolute value of the quantity x minus h, we're now squaring that difference. So for the vertex of a quadratic function, it's still going to be h comma k. The axis of symmetry is still going to be the line x equals h. The domain is all real numbers as well, because even though the lines are curved, they're going to continue on forever and ever in both directions. And the range is found the same way as the absolute value function. All you need to do is look at the y-coordinate of the vertex and then either include all the y values above if the graph is opening up or all the y values below if the graph is opening down. We're going to start first just by practicing graphing quadratic functions and filling in the table of values. For all these functions on this page, there are no h or k values. There are no values that are being added or subtracted to our function, and that means we're not shifting our function to the left, to the right, or up or down. This means that the vertex for all the functions on this page will just be 0, 0. If you're not sure, you can plug it into each function. So let's say if I look at this one, this is our parent function. If I plug in 0 in for x, to get my y value, that means I have to square 0. So 0 times 0 gives me 0. Picking another input value, if x is 1, then I'd square 1, which will give me 1 for the corresponding y value. If I want to find f of 2, I'd square 2, so 2 times 2 equals 4. Now using negative inputs, if we were to square a negative number, we would still end up with a positive answer, because a negative times a negative is a positive. So negative 1 times negative 1 equals 1, and negative 2 times negative 2 equals 4. When we graph and connect the points, we should end up with a parabola where it looks like the points on one side of the graph are reflected over the y-axis onto the other side. Now let's see how changing a, or changing the number that is multiplied by our parent function, will affect our function. Based on your knowledge of transformations, you can guess how the function will change before we graph it. Our vertex is still at the origin because we haven't shifted up, down, left, or right. You can also test it if we plug in 0 for x and square 0 and then multiply by 2, we're still going to get 0 because anything multiplied by 0 is still 0. Filling in these other values, basically we're getting all the output values that we got from our parent function, but then doubling it since we're multiplying it by 2. So hopefully you predicted this correctly, that this is a vertical stretch. When we compare the parent function to this function g of x, we can see that the function is a little bit more narrow. It's as if we took the sides of the parabola and stretched it upwards, and as a result, the two sides became closer together, or closer to the y-axis. We can describe these two parabolas as opening upwards. So you'll notice that regardless of whether input values or x values were positive or negative, our output values, or y values, were always positive, which is why we end up getting parabolas that look like this. So what would have to happen for us to get negative y values? How would that come about? So any number we square or raise to the second power, regardless of whether that number is positive or negative, we're going to get a positive number. So what has to happen for us to get a negative y value or a negative output is that we take that positive number and then multiply it by a negative number. So that means that a, or whatever our original function is multiplied by, that number would need to be negative for the parabola to open down. So we're going to try a few of those examples next. So this problem here is just like our parent function, but instead of it being all these positive y values, all the y values have now become negative because we're multiplying it by a negative 1. This means that we're taking our function and reflecting it over the x-axis, so it's flipped upside down. So we've seen a vertical stretch and a reflection over the x-axis. Now let's look at a vertical compression. So a vertical compression, our sides of the parabola will be a little further apart from each other and closer to the x-axis. It's as if we're smushing it down towards the x-axis. For the table of values, I have a few extra points in there, and the reason for that is because I know that I'm going to take my input value and square it and then multiply by 1/2, which is the same as dividing by 2. So anytime I have a number that's not divisible by 2 or it's not even, I'm going to end up with a fraction answer. So for example, my input values -1 and 1 gave me the output value 1/2. This is something that I can still graph. I have those points on my graph there, but it does get a little bit more tricky, especially when we start moving into transformations where we shift it up and down and left and right. So just so you're aware, you can pick and choose the values that you use as your input. So if I wanted to make sure that I didn't get any fraction answers and that all my outputs were integers, I would just have to make sure that all of my inputs or all of my x values were values that could be divisible by 2. Go ahead and graph number 5. For number 5, I used the same approach where I chose specific points that would only give me integer answers. So I jumped from having the input 0 to then 3 and 6. If I chose the input 1, I would end up getting 1, 1/3. If I chose the input 2, I would get the point 2, 4/3. So again, they're not like, you can still graph them. They're not impossible to graph, but I think it is a little nicer sometimes to just have those integer values to create a little cleaner of a graph. Number 6 is our last problem. Make a prediction about what you expect the graph to look like and what kind of transformations are happening. We're multiplying our parent function by -3. The 3 tells us that this is a vertical stretch, so it should be narrow. And the negative tells us that we are going to flip our function, that this is a reflection across the x-axis, so all the y values will be negative.